So as we jump into Module 5, we're going to continue on with torsion, looking at circular shafts, looking in particular at some stresses and some deformations. So this module is going to consider structural members and machine parts that are in torsion. We're going to take a look at the analysis and where the stresses and strains of the members of the circular cross-section are subjected to twisting couples or torques. So a couple of things we're going to look at this module here. We're going to review the concept of torsion that we've looked at before, now for structural members and machine parts. We're also going to review stress concentrations and look at how that they're included in torsion problems. From there, we're going to describe the elastoplastic response of circular shafts. So this is some new material there. And then go on to take a look at the torsion of non-circular members. So everything up to this point I'm looking at has been a circular member. Take a look at some non-circular member shapes. And then from there, I think the last topic will be looking at these thin-walled hollow shafts and define their behavior. So relating back to our textbook, this goes back to Chapter 3, Sections 5 to 10. So if you're looking back at your textbook, take a look at sections 5 through 10 within Chapter 3. So as we jump into Module 5.2, within this module here, we're going to take a look at torsion for shafts, looking particularly at residual stresses, non-circular members, and our thin-walled hollow shafts. So objectives within this module here, taking a look at these stress and deformations of circular shafts, then going on to elastoplastic material. From there, looking at torsion of non-circular members, and last, taking a look at thin-walled hollow shafts. So within this module, we're going to take a look at some of the key theories to go along with this, along with the governing equations, some practical applications, and from there go into some actual problem solving and some hand solutions. So next, let's take a look at stress concentrations. Before we get started here, we're going to go back and review our derivation of our torsion formula. So we can reference back in our textbook to equation 3.9 here, and we can see this relationship for our tau max right here with T sub C over J right there. This is for assumed circular shaft with uniform cross-section loaded through rigid end plates. Now, one thing to consider as we're looking at this here is that the use of flange couplings, gears, pulleys, and attachments to shafts by keys and keyways and cross-section discontinuities can cause these stress concentrations. So we can take a look at these coupling shafts up here in figure 3.26. We can see two different types. We can see the first one in part A here is a bolted flange. So there's that flange we're talking about right there. And then you can see in part B down here, we have the slot for a keyway right there. So these are some practical applications that you've seen before in a couple different types of scenarios. And both of these, again, they can see as we down here, these are going to lead to and cause stress concentrations. Now, one thing we got to think about these is as we're designing either the shafts with the bolted flange or the slotted keyway, is to think about the geometries and how that geometry and that shape is going to affect the stress concentrations. So one thing that we can take a look at down here from either experimental or some type of finite element analysis, type of numerical determination, you can figure out this concentration factor applied by equation 3.22 if we relate back to our textbook here, which you see is very similar to our 3.9, but now you can see we have this K factor in right there. So this, again, is our stress concentration factor, our K factor right there. Now, how does the stress concentration factor come into play with what we talked about for geometries here? Well, we can take a look over here at our figure 3.28, and we can see a plot of the stress concentration factors for fillets in circular shafts right here. So this is one right here. You see you have your outside diameter of your circular shaft right there. Then you have that radius in right here. Then you have that inner smaller diameter right there of lowercase d. Well, if you take this ratio of your larger d to your lower d right there, and then you take this ratio of your lowercase r, your radius right there, to this lower, smaller diameter right there, we can take a look here. So now the ratio between big D and little d right here, between the big and the small section diameters wise, you can see we have these different curves right here. So if you have a big D over little d of a 2.5, we're using this curve here, whereas if we have a 1.111, we're using this curve up here. Then we come down to the bottom and see where that curve intersects our r over d. That inner radius right there of that curve section cutting in like that with that small diameter right there. So we can take a look at that ratio. Let's just say this was 0.05 and we were at d over d of 1.111. We come over, okay, I'm using this curve here. Then I drop right down here all the way down to my, on the curve where it intersects with the 0.5. So I come down here like that. And then what I can say is, okay, if that 0.5 comes up, touches that curve there, then I have a K value here of about 1.42 roughly. So same type of thing for any other curve right here. Let's just say the D over D ratio was 2, and we had an R over D of a 0.15 right here. So we go over the 1.5, go up until we hit that curve. Then we come back over the side over here and say we'd be at a 1.32 in that case there. So that's how we're going to use this chart here from figure 3.28 in our textbook, along with our physical geometries right here, in order to calculate our K factor there. Now this is typically how we would use this. Now let's just say you had a problem though, and they're saying, hey, for a K factor of maybe 1.5, and you know that your big D and little d are this, what type of radius do you need? So then you can still do that, come over here, figure out that ratio of your big D and your little d, hit the right curve, come down, and you get your ratio of little r over little d right there, and your only unknown is the little r, plug in because you know your little d right there, and then you could back your r out, or for any of the other variables they're asking you for. So just another way that you could use this plot of stress concentration factors for these fillets and circular shafts. But again, this is just for fillets on circular shafts. So next I want to take a look at plastic deformations. So as we're looking at these, we're going to make the assumption that we're using a linearly elastic material. And if that's the case, we can go back to this relationship here that our tau max is equal to our Tc over J. Now the thing to note though here is if the yield strength is exceeded, which would take us out of the linear region, or the material involved is a brittle material with a nonlinear shearing stress strain curve. So we're looking at a nonlinear shearing stress strain curve, which we can see demonstrated over here in figure 3.30. Then these relationships are no longer valid. Now, shearing strain varies linearly regardless of your material properties. So the application of a shearing stress strain curve allows a determination of this stress distribution. Relating this to a governor equation, we can go back to 3.22 in our textbook right here, and the integral of the moments from the internal stress distributions, we're talking about an integral right here, is equal to, now we can find our torque on the shaft at that section. So we see the torque on the shaft at the section is equal to the integral from 0 to c. As we go back to our diagram here, we can see that c comes out right there to the outer radius, the outer edge of the circle right there. And that is times our rho t, so there's our rho value right there, times our tau value right there for our shear stress, times now 2 pi times rho d rho right there. So we can pull out our constants up from the integral right there. Say that that torque on the shaft at that section is equal to 2 pi, I'm going to pull out those constants, times the integral again from 0 to c, where c is that outer radius there, times our rho squared, when we see the rho in that row there, those go multiply through to make a rho squared, times our tau value there for our shear stress, dp, and again this relates back to equation 3.22 in our text. So now as we continue on, I want to take a look at our elastoplastic materials right here. So thing to think about when we're looking at this relates over here to our equations from 3.25 to 3.34 in our textbook here. And I want to mention this because the textbook does a really good job of the derivation of these equations and going through the explanation of how we derived and got down to this relationship in 3.34. So I would highly recommend going back to your textbook and looking at the detailed information on how to derive these equations and how they actually work together. So with that being said, what I want to take a look at here is we start at the beginning of 3.25. We'll take a look at the maximum elastic torque, or T sub y right here. This is equal to J, our polar moment of inertia right here, divided by C, where this is the outer radius C right here, we can see on our diagram there, times our T sub y, our yield strength right here. And this is equal to, this is where we come up with and do our first derivation to get to equation 3.26. And again, the textbook talks about how we can plug in for that there. So we can see the same thing. Here we have our T sub y, our tau sub y right there. But what we see now is this 1/2 pi c cubed is a replacement here for a relationship for J over C there. And again, the textbook goes through that a little bit for that derivation. Comes up with a relationship for 3.26. And then we can see we have this relationship here from before of the angle of twist. Our angle of twist at the onset yield, our T sub y. Now this is equal to L, our length there, times our strain, our yield strain there, divided by that C again. That C is that distance out here, our outer radius right there, or a circular shaft there. So now as the torque is increased, in a plastic region right here, this plastic region is going to develop this tau is equal to tau y, or our shearing stress equal to yield strength right there around an elastic core right there. So then we have this relationship here that our shear stress right here is equal to our rho over rho sub y times our tau sub y right there, which again leads us into this relationship that we see down here. We can derive equation 3.31 in our textbook. There we have a rho sub y is equal to that L times our sigma y over our phi right there, and that's by using this relationship up here for our angle of twist as well. So again, please reference back for the detailed information step by step on how to break this down in the textbook there. Then we get in here, our torque is equal to 2/3 our pi c cubed times our tau y times 1 minus 1/4 of our rho y to the fourth over c, or to the third over c to the third. We can break that down, simplify it a little bit, and we end up with 4/3 ty times 1 minus 1/4 of our rho y to the third over c to the third right there. Plug in this relationship that we see that we can relate again back from this equation right here. We can plug in, rearrange slightly, and that's where we come up with our equation 3.34 in our textbook for torque is equal to 4/3 times our t sub y right there. And again, we recall that from up here from 3.25 times 1 minus 1/4. Now our angle of twist y, t sub y here to the third over theta to the third right there. So again, this references back to equation 3.34 in our textbook. So now as our rho sub y right here approaches 0, the torque approaches this limiting value right here, then our T sub p, or our plastic torque, is equal to 4/3 ty. And that's again because if this rho sub y right there were to approach that 0 right there, this would go to 0, dropping that term right out there. So this would just be 1 minus 0 right there. So then you would see you would just have, if you go over this relationship here, if this whole thing goes to 0 as our rho sub y goes to 0 right there, then you're just left with this ratio right here of your 4/3 ty. So this is your plastic torque right here as your rho sub y approaches 0. Now this is something I want to mention. You can simplify these down, and again, that's another reason why I encourage you to go through this derivation in the textbook and understand how we get these formulas, not just plug in, okay, that's what I get for plastic torque. Understand why. And it's because this is approaching 0. The torque approaches this limiting value right here, and that simplifies this portion of the equation down right there. So you're not just picking a very specified equation right there and just plugging into it and spitting out your answer. You're understanding the derivation from your very general basic equation, applying some of the other equations we've seen along the way, working down through it, seeing where things cancel out and simplify, applying these conditions right here and these limiting values to get what we need to do. So again, take a minute, look back, go through the derivations, and don't just blindly plug and chug through these equations. Other thing to remember here is this is valid only for a circular solid shaft right there made of an elastoplastic material. So there's a lot of things right there that make an assumption. It needs to be circular, it needs to be solid, it needs to be elastoplastic material in order to use this relationship. Now let's take a look and see how this stress-strain distribution looks right here over in figure 3.34 for elastoplastic, perfectly plastic shaft in different stages of loading right here. So we can see in part A, we have elastic. Part B right here, we have an impending yield right there. And part C, we have partially yielded. And in part D, we have fully yielded. And we can see, again, how this stress-strain distribution looks for each of these different stages of our loading right there as we go along. So a way to think about this is kind of relate back to just a simple tension test right there. So you start pulling it here, you stay in that perfectly elastic region. You can see right there, you're in that perfectly elastic region there. Then once you start to get to impending yield, you start to see it come up here like that, impending yield. This is where your tau max is equal to your tau y right there. So right here for this relationship right there. Then you get to part C right here. It's partially yielded right there. You can see that kind of levels off right there. And then last, once you're fully yielded, you have this relationship right there. So that kind of, again, just thinking about it as you're pulling on a tension test, a sample specimen, a dog bone, if you will. This is kind of what we think. You go from elastic, impending yield, partially yield, fully yield. So next I want to take a look at residual stresses right here. So if we take a look at figure 3.37, we can see the shear stress restraint response for loading past yielding reversing until compressive yielding occurs. Now if we take a look at this graph, we have a typical stress strain graph. We have our strain over here on the x-axis, our stress up here on the y-axis. We can see we loaded up past our yielding point. And what we can note here is that the shearing stress will continue to decrease when we unload it. Until it reaches a value equal to its maximum value at C minus twice the yield strength of the material. So that's where we get this twice the yield strength of the material right here. Here's our 2 times tau sub y, our yield strength right there. So it's going to keep decreasing right here. There you see that linear decrease until you hit that tau ty, then we start to see it curve over right here. So now one thing we want to consider here is our plastic region. This plastic region is going to develop in a shaft when it's subjected to a large enough torque. So we're going to stay in our linear region until we hit a large enough torque, then it's going to take us into that plastic region and out of the elastic region there. So then once we've gotten up to that large enough torque, we've got developed into our plastic region there, we remove the torque, and once this torque is removed, the reduction of stress and strain at each point takes place along a straight line to a generally non-zero residual stress. So it's going to be a non-zero residual stress because we've taken above and gone into our plastic region, then removed the torque there. So if we take a look at this relationship on a torque and angle of twist curve, a Thie curve right there, the shaft unloads along a straight line to an angle greater than zero when we're looking at our twist. So we can see here, here's our torque and our angle of twist right there. You can see we load this up along a linear line there, go past our elastic region into our plastic region where we develop our plastic region right there, and then in what case we unload the curve right there. So again, we remove the torque right there, and we can follow this reduction of stress down here, and as it says, it goes along a straight line to, so we follow it down a straight line right here to a non-zero residual stress, which is where we end up right here. So now we can see here at that point right there, this distance from our 0 point at the beginning there, we can see this Thie sub P. Now this Thie sub P is our permanent twist. Now if we go back to equation 3.35 in our textbook, we can see a relationship right here for our permanent twist relative to our loading phase and our unloading phase right there. So the permanent twist is equal to our loading phase minus our unloading phase there. So Thie sub P is equal to Thie minus Thie prime right there. So we can see, okay, there's our Thie sub P, and this is equal to our Thie right there, our loading phase. So we can see that goes from there right there to 0 all the way up to where we loaded right there. Some total torque, T right there, minus our unloading phase right here. So we unload it. There's our distance to our unloading phase right there. So we can see loading phase, angle of twist from our loading phase, minus our angle of twist right here from our unloading phase right there is equal to, what we're left with now, once we load it and then unload it, is what's a permanent twist, or our Thie sub P. So now let's continue on with our residual stresses. Now, our residual stresses are found from the principle of superpositions. This principle of superpositions is illustrated down below here in figure 3.39, where we see that our superposition of the elastic plastic state, right here in A, this is our elastic plastic state, plus the linear elastic unloading, which is shown right here in figure B, our unloading right there, is equal to, we can see over here in C, our sharing stress distributions over here. So this relates back to equations 3.9 in our textbook right there. We have our T sub M is equal to TC over J, where now we can see that our T prime M, as we modify it here, is the maximum stress in the distribution of the reverse stresses. And this is equal to, again, TC over J, where T is the torque, C is that outer radius right there, and J is our polar moment of inertia there. We also have the relationship shown here in equation 3.36, where we have that integral of rho right there, our x-axis right there, times our tau dA is equal to 0. So if we take a little bit closer look at this diagram here, okay, we start A plus B, or elastic plastic state, plus our linear elastic state, and B is equal to C over here, our sharing stress distribution over here. So let's just take a look at each of these separately right here. So if we go to A, this is our elastic plastic state right there. So you can see, okay, there's our elastic region that we saw earlier right there, going up along that, and then we get to our, once we hit here, our plastic region right there, and there's our tau sub y right there. You'll see this distance in the linear region, or the elastic region right here. There's our rho sub y right there, and we had those governing equations we saw earlier in this module for that there. So this right here plus our linear elastic unloading. So this is where we unload this here, so we show this down here like this right here, going out again to our outer radius. There's C right there, and this right here is equal to that. This is our maximum stress in the distribution of the reverse stresses right there. So we can see that relationship right there from that governing equation, which is a modification of equation 3.9 in our textbook. So you add those two together, so this area there along with this area there, and we end up with this sharing stress distribution over here, where we have this relationship we see graphically over here, where there's our rho on our x-axis, there's our tau up here on our y-axis right there. Now we see if we go out to that rho sub y right there, that same distance right there, we see it loading up to there, all the way out to our point C right there. So this is just a visual representation, and we'll go on to do an example problem utilizing some of this visual representation in order to find our residual stresses from this principle of superposition. So now let's take a look at a problem that shows the application of some of these concepts and governing equations we looked at within this module here. So if we look at concept application 3.8 and 3.9 from our textbook right here, what we have is they tell us that we have a solid circular shaft, and the shaft is going to be subjected to a torque. Now they give us a value for this torque of T is equal to 4.6 kilonewton meters at each end. So we come down here, see our diagram here, there's our 4.6 kilonewton meters at each end of the shaft right here. Now they then tell us to assume that the shaft is made of an elastoplastic material, and they give us that T sub y is equal to 150 megapascals. Our shear modulus G is 77 gigapascals. And then they ask us to find 4 different things within this problem right here. So the first thing they want us to find is they want us to determine the radius of the elastic core. Then they want us to find the angle of twist of the shaft. From there, they tell us that when the torque is removed, they then want us to find part C. They want us to determine that permanent twist right there. And then lastly, they want us to find the distribution of the residual stresses. So these are all things that we've just looked at the governing equations, saw a couple ways that we can apply those equations there to a problem like this. So now what I'd like to do is take a look at this and think about, okay, how am I going to go about solving it? Let's actually twist the shaft, think about what's happening here, think about all of the information they gave us in the problem statement, use that to come up with our setup page. We write down everything that's given to us, everything they want us to solve for, and any assumptions that we're going to make. So as I'm looking through this and thinking about the problem, I'm physically twisting this, okay, I can also see in my diagram, not only do I have my torque at each end, but I also have the whole length of the shaft here of 1.2 meters. I have the diameter of my shaft here of 50 millimeters, and it's a loaded circular shaft. So as I think about my solution, how I want to solve it, I think about some governing equations I might want to use, thinking, okay, maybe 3.29, I can use this right here to evaluate the elastic core radius, because in part A they did tell me I needed to solve for the elastic core radius right there, so I have that rho sub y right there, and I have my C value there, okay. Now I think I can come back and solve that, and then I think of my angle of twist, was part B they asked to solve for. I know I have a governing equation for my angle of twist, and somebody's going to be untwisted there, so I can go back to equation 3.16, find the angle which the shaft untwists when the torque is removed. They tell us the torque is going to be removed. And from that, I can then get my permanent twist that they asked me to solve for, which I recall, again, that's the difference between the angles of the twist and the untwist. And finally, I remember in the last part they asked me to solve for here for residual stresses and the distribution, we could use that superposition that we looked at earlier in the module there of the stress due to twisting and untwisting the shaft. This is just kind of all playing out in my mind right now as I'm thinking about all those 4 things they asked me to solve for, all the things that we've looked at in the module, everything that's given in my problem statement and initial diagram. So now I want to take and actually organize that in a manner that I can come back to and pull off my givens, take a look at what they asked me to solve for, plug into governing equations. So this is why I want to take this information, this kind of thought process in my head, and create that setup page. So that's exactly what I do right now, is I create that setup page there. Okay, I say this is problem 3.8. Here's a simplified version of my given diagram over here. I have my 2 torques applied at the end of my length L there. Now you can notice what I did is I take that initial diagram that they had there. I no longer have my values in it there. I've just replaced this just as my torque, my length L right there. Then I come over here and I create my givens. Again, with the givens, you want those 4 different things. You want the variable name, you want the numerical value for it, you want the units that you're using, and you want a description of how it relates back to your problem. So you get all 4 of those things. There's your variable name is L. L is the shaft length right there. 1.2 is the numerical value. M is your meters or your units right there. So I have the variable name, the numeric value, the units, how it relates back to my physical problem right there. So that's the shaft length there. Do the same thing over here for my shaft diameter. Variable name is D. That's 50 millimeters, and that's both those 2 are given within the actual diagram and not the problem statement there. Then I have my torque, which is in the problem statement and in the diagram as well, is T, and this is equal to 4.6 kilonewton meters. Again, I have my units down there. I'm double checking my units. I have my yield strength and shear, or my tau sub y, which they give me in the problem statement, 150 megapascals, and I have my shear modulus or modulus of rigidity right here of 77 GPa. Now, they want us to find 4 different things. I clearly write these out. Now, not only do I separate these out as A, B, C, and D, so I can come back and make sure I'm solving every single thing they asked for, but I have written out what they asked. The radius of the elastic core, what is that variable? That variable is my rho sub y right there. My angle of twist, that variable I'm solving for is my phi. permanent twist, well, that's my phi sub p. And then lastly, I have my distribution of the residual stresses right there, which is going to be that diagram that we're going to draw, similar to what we saw earlier within this module there. So now I've created my setup page. I've read through my entire problem statement, looked at the initial given diagram, figured out exactly what they want me to solve for, exactly what they've given me, have a slight plan of attack in the back of my head for at least some governing equations, how I'm going to start solving this. So from there, I want to solve each of these. I'm going to break it down into individual parts. I'm just going to look at part A. So this is my solution here. Just looking at part A of my solution right here. Well, I want a governing equation. Look at what they give me, what they're asking me to solve for, come up with what equation is going to help me get there. Well, we came up with a derivation of this equation within our module here. So this is equation 3.29 in our textbook back on page 198. And we can see here that torque T is equal to 4/3 my T sub y times 1 minus 1/4 my rho sub y to the third times c to the third right there. Well, I want to solve for this right here. I want to solve for my rho sub y over c so I can get that radius I'm looking for in my problem statement there. So I solved this out. So I basically just rearranged this. So I want to go through and do this step by step, make sure I do this right. Start with that governing equation 3.29 from 198 in our text, and I say, okay, first thing I'm going to do right here is I'm going to divide both sides by this 4/3 T sub y right there. So I do that, divide both sides by that. I even make a little note that this is what I'm doing. I'm dividing both sides by this 4/3 T sub y. I do that there, and I see, okay, now I have my T, my torque over my 4/3 T sub y is equal to 1 minus 1/4 times now I have my rho sub y to the third and c to the third there. So I'm thinking, like, if I wanted to get this by itself, okay, I got to move some other things around. So I'm going to rearrange this here. So the first thing I'm going to do is I'm going to come over here. I'm going to pull out a 3/4 out in front of here. So rearrange this 4/3. I can put this out. And this is a 3/4, and I can pull that out in front of this right here. So now with that there, I have 3/4 times my T over T sub y is equal to 1 minus 1/4 times my rho to the rho sub y to the third over c to the third right there. And then I want to think about, okay, now that I've got that there and I want to get this part right here on its own, what's the next thing that I want to do? So the next thing that I want to do is I want to add 1/4 of rho y to the third over c to the third right there to both sides. Now, I don't have to do it that way. There's other ways that I could have done this. I could have moved this 1 over here and subtracted it, but then I would have been left with a negative here, and I just didn't want to deal with the issues of dropping a negative and sign convention, all that. So I decided to move this all over to the other side, eliminate the negative by adding this over here. So then what I end up with when I add that over there, the only thing left on this side is a 1. So I have 3/4 times my T over T sub y plus 1/4 of this rho sub y to the third, c to the third right there is equal to 1 right there. So then what I want to do now is I'm going to go ahead and look at this right here, and I can say, well, I've got this right here. Let's get that on the other side to get this by itself right there. So I subtract this over the other side there, say minus 3/4 of T over Ty minus 3/4 of T over Ty there. And it leaves me just now with this 1/4 rho y to the third over c to the third right there is equal to 1 minus, and I have this over here now, 3/4 of T over T sub y right there. So I want to say, okay, let's get rid of that quarter. Let's divide by a quarter there, divide by a quarter there, and I even say this out here, I'm dividing by 1/4. I put that over the other side. Well, I divide by a quarter here, it eliminates it completely. I'm just left with this guy here. Then I divide this side by a quarter over here, and 1 over 1/4 is just 1 over 1/4 right there, which goes to a 4. Right there, and when I say 3/4 divided by 1/4, that goes to a 3 right there when I do out the math there. So then what I'm left with my rho y to the third over cy is equal to 4 minus 3 times my t over ty. Well, then I see, okay, well, what I want to do is I want to get rid of that cubed right there. So I'll take the cubed root of both sides right there. So I take the cubed root of both sides right there, like that, and I make a little note. That's what I'm doing over there. When I take the cubed root of that side right there, it gets rid of both the cubes. I'm just left with exactly what I wanted to solve for there. My rho sub y over c. This is equal to the cubed root of 4 minus 3 times my t over ty. So now I have a relationship right here to solve for my rho y over c. So from there, how do we solve this for my t sub y? So I take a look at this, and this is we can go back now here and say, well, if I need a value for that there, I can look back to equation 3.25 on page 198 of our textbook. We have T sub y is equal to J over C times my tau sub y. So now we need a relationship for T right there. Well, I can say, let's see, now I have my polar moment of inertia, my J value right there has its own expression right here of equal to, for a solid circular shaft, which is told me in the problem statement, my polar moment of inertia, my J value is 1/2 pi c to the 4th. where then C still relates back to the D in my problem right here, where your C is your radius, your outer radius right there. Radius is half of your diameter right there. My diameter is 50 millimeters or 0.05 meters. I can plug that right there into this relationship here, take half of that, and that'll equal my C value. So C is equal to 1/2 of 0.05 meters. So C is equal to 0.025 meters. So now I have a value for C that I can plug back in here to get my J. So J is equal to 1/2 pi times that value for C now there, which we just solved for 0.025 meters, solve to the fourth, double check your units right there, do out your math. Now you have a numerical value for J. J is equal to 614 times 10 to the negative 9 meters to the fourth. Is that the correct units for J? For, again, here, your polar moment of inertia? Yes, it is. It should be in meters to the fourth right there. So now that I have a numerical value for J, I can plug that back up in here to solve right here for this relationship for my T sub Y there. So that's what I do. I go back to that governing equation for my T sub Y right there, and I say, okay, where? I look back at my setup page right there. Well, this was given to me right there in the problem statement. My tau sub Y is equal to 150 megapascals. If I just want to deal with this in pascals, it's 150 times 10 to the 6 pascals. I have my C value that I just solved for my diameter there. This is equal to 0.025 meters. And now I've just solved for my J value there. My J is 614 times 10 to the negative 9th meters to the fourth. So I can plug my J value in there. I can plug my C value in there. And I can plug my tau sub Y value in right there, all in the correct units. Plug those in. And what we end up with is T sub Y is equal to, well, there's my value right here now. There's my tau sub Y right there. There's my J value right there, 614 times 10 to the negative 9th meters to the fourth. And then on the bottom, I have my C value right there, which is 25 times 10 to the negative third meters. Pascals, meters to the fourth, meters right there. We can take a look at all of this right now. What we find out with when we do that out, or do our unit analysis for each of those, we end up with T sub Y is equal to 3.68 in units of kilonewtons per meter. Do those meters check out? Yes, they do. Those units check out. That is correct, what we'd expect for our T sub Y for those units. And then from that there, we recall, well, now we can go back, now that we have my T sub Y, do all that extra stuff there, we can go back in and solve for our equation for my rho Y over C, which we're looking for that radius there. Now, the reason I did this way is because you're not always going to see 10 steps ahead. No, okay, I needed to start with this equation here. I actually need to start with my J equation first. No, you're going to see your general equation, and then you say, like, well, I don't have this and this. What is a governing equation for that if I do have this, this, and this? Which, again, really emphasizes the fact of setting up that setup page at the beginning so you can clearly look and see what you have, what units they're in, what they're asking for, and what you can use for equations. So you can see here, it's not just the one governing equation, but that one governing equation that we used had many other sub-equations that we needed to plug in for in order to solve for those unknowns to get back to that governing equation to get to what they actually asked us to solve for in that part of the problem. So now we can go back to this relationship we had for our rho sub Y over C that we saw that was equal to 4 minus 3 times T over Ty to the 1/3 right there. But now we have these values here. We have a T value, we have a T sub Y value. Our T was 4.6 kilonewton meters, and our T sub Y was 3.68 kilonewton meters there. So we can take those and plug them in for our T and our T sub Y right there in this equation. When we do that, we see that rho sub Y over C is equal to 4 minus 3 times, now we plug in right there, 4.6 over 3.68, all the 1/3. So those are all numeric values. So we can get a numeric value when we plug those in for our rho sub Y over C. I'm going to leave that there for now. There's a reason why I solve this later, and we'll see as we get to other parts of the problem, why it's nice to have this value of rho sub Y over C before just solving for our rho sub Y, which was our radius of the elastic core, which was they asked us to solve for in part A. We might need this a little later. This might not be something you foresee looking at all the other parts, but to tell you a reason why I left this as rho sub Y over C and didn't plug this C in right away and waited. So I got this value right here. Now rho sub Y over C is equal to 0.63, which I'll keep in the back of my mind. But I know my C is equal to 0.025 meters, so I can plug that in for my C value right there. Now my rho sub Y, my radius of the elastic core, is equal to that ratio of rho sub Y over C times C right there of 0.025. Plug that in, we end up with our rho sub Y. We convert back to millimeters here. Was 15.8 millimeters right there. So that's part A that they asked us to solve for in this problem, was our rho sub Y, our radius of the elastic core. So moving on from there, we can now solve for part B. What did part B ask us to solve for? Well, they want us to solve for that angle of twist. So we can start with a governing equation for an angle of twist. we can go back to equation 3.15 on page 168 of our textbook right here, and we have that phi, or our angle of twist, is equal to T times L, our torque, times our length over our polar moment of inertia J, times our shear modulus, or modulus rigidity here G, and we write that as our governing equation. For our problem here, we want to solve for our T sub y right there, and this is going to be our T sub y there, our L, our J, and our G right there. So again, we start with our general equation, tweaked it slightly for our problem right here we're solving for, and then we wrote back to our setup page and everything else we solved for. Well, I have a value for T sub y. That I've solved for, that's 3.68 times 10 to the third Newton meters. I know L is given to me in that initial diagram of 1.2 meters, and that's right from my setup page as well. My polar moment of inertia I've just solved for, that's 614 times 10 to the negative 9th meters to the fourth. And my modulus of rigidity is given to me in the problem statement of 77 times 10 to the 9th pascals. Plug all those in. There goes my G there. Plug in my J over here. Plug in my value for L here, and plug in my value for T sub y up there. Those are all numeric values. So from that there, when I plug in, I end up with my T sub y right here, that angle of twist right there they're asking us to solve for. Plug that in. This is 3.68 times 10 to the third kilonewtons right there for my T sub y. So kilonewton meters right there for my T sub, Newton meters, not kilonewton meters, Newton meters right there for my T sub y, times my length L in meters. And then I come down here to my J value here, 614 times 10 to the negative 9th meters to the fourth. And then I have my 77 times 10 to the 9th pascal. So as you can see, even as I'm talking through it, I might say the wrong unit. So that's why it is important to write out what your units are each step along the way. And you don't accidentally write down what's in your mind by accident. You double check that. Do your unit analysis out. Make sure you end up with the right units at the end that you should expect for this. We would expect radians for this, which we do when we do our unit analysis for this. And it's easy to do the unit analysis when we write it. Newton meters, meters to the fourth, pascals. What is a pascal? Put those values in. Cancel out everything that cancels out. See what you're left with, and is that what you would expect for the variable that you're solving for? In this case, yes, it is. We want this in radians. We end up at T sub y when we do our math out is 93.4 times 10 to the negative third radian. So now that's our T sub y. We want to solve for phi, our angle of twist, is what they asked us to solve for in this part of the problem right here. So in order to do that, what we want to do is we go back to equation 3.33 on page 199 of our textbook there. Now we see we have this r sub y over c is equal to T sub y over phi. So with that there, we can then rearrange this to solve for phi right there. And that's why now you can see we already solved for this phi sub, rho sub y over c of 0.63. So I can plug that right in now to the denominator right there. And I've already thought of my phi sub y right there, which I can plug right into my numerator there and get my phi value out like this. So phi is equal to, now when I plug that in, 93.4 times 10 to the negative third radians divided by 0.63. On the bottom here, which is the ratio there. We do that out, and that's unitless there. What we end up with, phi is equal to 148.3 times 10 to the negative third radians. So this is all in radians right now. If we did want to convert to degrees, what we do is just say, okay, phi is equal to, and I do out my full unit analysis here. Sometimes you get confused, wait, was it 2 pi over 360 or 360 over 2 pi, or just multiply by 360? What is it? Well, we just say here, 2 pi radians is 360 degrees. So we can plug that right in there. Our radians are going to cancel with our radians right here. So we'll end up with just saying this right here, if we do this out, we'll divide by this 2 pi radians right there times 360 degrees. What we end up with is that phi is equal to 8.5 degrees, which is our angle of twist. So now we've answered part A and part B for this problem here, which is 3.8 in our textbook. We go on from there to go to 3.9 sample problem in our textbook here, which is the beginning of part C of this problem here, which now they'd asked us to go forward and find the permanent twist. So if we go back, we can still go back to our governing equation we lose in the last section here, 3.15 on page 168 of our textbook there, where we have our angle of twist is equal to T times L, our torque times that length, all over J times G, where J is our polar moment of inertia and G is our modulus rigidity right there. So we can solve that there for our phi right there and come back to it. What we also need to see here is the permanent twist is the difference between the angles of twist and untwist. So that goes to this governing equation right here. Our phi sub p, right there, our permanent twist, is equal to phi minus phi prime, where phi is our twist and phi prime is our untwist right there. So we've already got a value for twist. What is our untwist? Well, that's where we can go back to that 3.5 again, but now for our problem here, it'd be phi prime is equal to t over T times L over JG there, where T now is, for our untwist right here, our torque right here is 4.6 times 10 to the third Newton meters that we had before. So now we plug that value in for T. So that's the main difference there from what we plugged in before. And we have our L is the same, length doesn't change, it's still 1.2 meters. Our J doesn't change for our polar moment of inertia, it's still 614 times 10 to the negative ninth meters to the fourth. And our modular rigidity remains the same for this, is 77 times 10 to the ninth pascals. Our only thing that changes right here is that torque for our untwist right there. Plug in those values, we see that our untwist, our phi prime, our angle of untwist right there is equal to, now what we have here, 4.6 times 10 to the third Newton meters times a length of 1.2 meters divided by our polar moment of inertia and our modular rigidity right there. Plug in those values, we end up with phi prime is equal to 116 times 10 to the negative third, again in units of radians. Double check your unit analysis, make sure you do everything right. Newtons, meters, nothing's in millimeters right there. That's in pascals, not gigapascals. That's in newtons, not kilonewtons there. Okay, everything checks. I do end up with radians at the end. It's a great double check with that unit analysis. So from there, if we did want this in degrees again as well, we then use that same conversion right there. If this is in radians there, we know it's 360 degrees for 2 pi radians right there. Radians cancel with our radians there. We're just left with degrees as our units. Do our math out, we end up with phi prime is equal to 6.69 degrees. So now we have a value for our twist and our angle of twist and our angle of untwist right here. So our permanent twist is the difference between our twist and our untwist angles there, where our twist angle was 8.5 degrees and our untwist angle was 6.69 degrees. Plug that in there. Plug this in over here. We say our permanent twist theta sub p is equal to 8.5 minus 6.69, all in degrees. So therefore, our theta sub p is equal to 1.81 degrees, which is what they'd ask us to solve for in part C, our permanent twist. So now we go back to our setup page and we look, okay, is there anything I haven't solved for yet? Well, yes, there's still this fourth part, part D right here, where they want us to find our residual stress distribution. So with this here, we're actually going to need to draw out some stuff, as we saw earlier when we went through the beginning of this module here. We'll need to actually draw out some of this stuff for that stress distribution. We ask ourselves, what do we know? Well, T sub y, our yield strength here, was given to us 150 megapascals, and our radius of the elastic core we'd solve for in part A, that was 15.8 millimeters. Again, pay attention to our units right here. This is in millimeters that we solved that for. And we need to find the max in the distribution of the reverse stresses. So from this here, what we can do is, again, go back to that governing equation 3.9 on page 156 of our textbook there, where tau is equal to T times C over J. In this case here, we want our tau prime max right here to find that reverse stresses, the max reverse stresses in the distribution right there, where our T we've already solved for, that's 4.6 times 10 to the negative, times 10 to the third, positive third Newton meters. Our C is that outer radius, 25 times 10 to the negative third meters. J is our polar moment of inertia, that's 614 times 10 to the negative 9th meters to the fourth. Take those values, plug them into this equation right there. We have all those numeric values, we can plug them right in. So we can then get a numeric value right here for that max in the distribution of the reverse stresses there, our tau prime max. This is equal to, we plug it in, 4.6 times 10 to the third Newton meters times 25 times 10 to the negative third meters, divided by 614 times 10 to the negative 9th meters to the fourth. Do out our unit analysis, see what cancels there. What we're left with is units of megapascals. So we got 187.3 megapascals for our tau prime max. So this is one of the things we're going to utilize as we're drawing out this residual stress distribution. So now we can begin to sketch out that distribution of stresses. We take that value for our tau sub y that we just solved for and plug it in right here. So recall that for superposition of the elastic plastic state plus the linear elastic loading equals the residual stress distribution. So we have here our elastic plastic state right here, and we have plus our linear elastic unloading over here. And this is equal to what we asked us to solve for in the problem right here, our residual sharing stress distribution. So that's what we wanted to see right here, is that stress distributions right there. So that's what we want to solve for. So we do the first two graphs out first right here, first two diagrams out first right here. We can see that we can plug in, here's our circle of our shaft showing our outer radius right here, which is C value of 25 millimeters. Pay attention, we're going to use some millimeters here. And then we had our radius of the elastic core, our rho sub y right there, 15.8 millimeters right there. So we can see that goes into there. So we have this linear elastic region that goes right up there until we hit to that 15.8 right there. Then it levels off at that 150 right there until we get to the outside right there at 25 millimeters. Then we do our unloading here, our linear elastic unloading. So we can see right here, we unload it. right there, all the way up to the outer value for our rho right there, and equal to C right there. And we can see what values we are. Well, when we get to right here, where we want to figure out what this value is down here for our tau prime right there. Well, how we do that right there is we say, okay, this is our 4.6 right there from that governing equation, times our 15.8 divided by our 16.4. That's our C value, that's our J value, and that's our torque value right there, torque, C, J value right there. We do that out. We find out when we end up at that C value right there, the radius right there, when we're at that radius of the elastic core right there, we end up with our tau prime value of negative 118.4 megapascal. So that's how we get that value right here. And then this value over here is that negative 187.3, which we solved for. That was our tau prime max that we just solved for before. So that's when we get down and we get to that value right here, and we have a C value all the way out there at 0.025 meters or 25 millimeters right there. So those are those two values right there on our tau axis right there. So you add these two together, and this is where you come up with this stress distribution diagram over here on the right. So we do that out and we say, okay, now 150 right here, tau sub y minus our tau prime right there, our 118.4 is our 31.6 right there. So if we go up there, right there, when we're at our value of 15.8, that radius right there, our radius of elastic core right there, we end up with over here on our graph a value, if we come over to tau right there, 31.6. Then we say 150 minus our 187.3. Well, that comes down here to a value, when we're at our value of C over here, if we come over to our tau axis right there of 37.3, that's our 150 minus 187.3. So we draw that out, that's our shear right there. We draw that out right there as a distribution, and that's what we end up with that graph right there. So this is the final answer that they had asked us to solve for. I can go ahead and erase my chicken scratch over the top of it, and this right here is what they'd asked us to solve for in this. So up until this point in the chapter, we've really only taken a look at circular cross sections here. So what if we have torsion of a non-circular member right here? So the previous torsion formulas are only valid for axisymmetric and circular shafts. So if we're dealing with a planar cross-section of a non-circular shaft, it does not remain planar, and stress and strain distributions do not vary linearly. So for uniform rectangular cross-sections, as we can see over here in figure 3.44, what we have here is we have these following relationships here, where tau max is equal to our torque divided by C1 over AB squared. So our tau max is equal to torque divided by C1, where C1 is the coefficient of the rectangular bar and torsion right there. And A and B, where A is our width right here and B is our height right here for this given rectangle there. Now for our angle of twist, we have this relationship here that B is equal to T times L, where L is still the length of this rectangular member right here, all divided by C2, which is another coefficient of rectangular bars and torsion right there, which we'll get to with a graph or some values for that in a bit right there. This is times AB to the third times G right there. So this right here is for phi, for angle of twist. This is our tau sub max right there for these uniform rectangular cross sections there. Another thing to note is that large values of this A and B right here, the maximum shear stress and the angle of twist for other open sections are the same as the rectangular bar. And we can see up here back in 3.41, this is what it looks like a little bit different when we're applying this torque for the twisting of a shaft with a square or non-circular cross section. So here's the chart we talked about here. This is for torsion of non-circular members. We saw these C1 and these C2, and we look at this values for A over B right here within this right here. So this is our coefficients of the rectangular bar and torsion right here. So for if we have a ratio from that A to B of 1, well, then these are our values for our C1 and our C2 right there. Now let's just say we had a value of 2 right here for our A over B ratio right there. Well, these are our corresponding C1 and C2. So this is what we'll use as we go up here all the way up through, and this just is up to 10 for that there, and then we can see for infinity right there, we end up with 0.333, so this is what it approaches as we get towards infinity there. So the next thing we're going to take a look at here is our thin-walled hollow shafts. So we can see over here in figure 3.47, we have a thin-walled hollow shaft subject to torsional loading. So it's the same type of diagram we've seen before for our circular shafts, and now we've seen it for our non-circular shafts right there. But now for these thin-walled ones, what else is different right here? Well, we have our torsion on the end, torsion on the ends right there. That's the same there. But now we can see we have the thickness here because it's a thin-walled hollow shaft. So that equates right there. The T value there is the thickness of that outer shell right there, or the thin wall on our shaft, and then from that there we want to take an element out. So we can see we have from A to B right here, we have element A, B right there, and it's some width right here of a delta X right there. So then we can see we move that element over here and just figure 3.48, zoom in out a little bit. This is a segment of that thin-walled hollow shaft of area of interest right there. We can see we have some values. Well, we have the thickness at the top at B, we have the thickness at the bottom at A, maybe it's uniform, maybe it's not right there. We have the width of this sample right here of delta X that we cut out right there. And then at those two areas right there from the torsion, what we have is we have our forces right here, shear forces are F sub B and our F sub A right there. Then we make sure we know which our direction X is right here, back to our corresponding X axis right there. Now we can see if we move down here to figure 3.51, what this is showing is our shear flow, our Q value right there in the member wall right there. So we're looking at a side angle right here. So if we're coming with the top one in 3D right here, kind of look at it from the side, you can see where that element AB is right there. So there's your thickness right there, the thickness of the wall right there, of the thin wall right there of your T, and there's your D sub S right there of that segment right there. And we can see coming off of this here, you have this distance P out here. It goes out at 90 degrees coming down to the center of that individual segment that we're looking at right there. Now, if we're talking about the area for shear flow, what that physically looks like is shown here in figure 3.53, where we go out to the center of that element right there, where that distance P is right there, and we come out everything within that. We see that dotted line as we draw it all the way around this. Everything in there in that shaded area up to that dotted line right there is the area for our shear flow. So now what we can do is take a look at our summing forces on the segment AB right here. So we can go back to figure 3.48. We have the segment from the thin-walled hollow shaft right here. So we have this described here. What we want to do is take a look at what our forces are. So we can see right here we have a force A and a force B right there. And we have this thickness of the element and the thickness of the element there. So what are the forces acting in the X direction? Because the X direction we say is positive in this way, so we're going to have a positive force FA and a negative force FB. Well, FA and FB can be expressed as the product of the longitudinal shearing stresses and the area of the face right there. Well, the area of the face, if we take a look at this, well, our TB and our delta X, our TA and our delta X are going to be those areas right there of the face. So, and then we have this is times our longitudinal shearing stress. So for A right here, our longitudinal shearing stress is our tau sub A, and our area of the face is that thickness A times our delta X right there. So that's our FA right there, going in the positive direction. Now in the negative direction, we have our FB right here. Well, our cross-sectional area there of our face right there is our thickness of B right there, our T sub B, times our delta X down here right there. So there's our area there, and our shearing stress right there, our longitudinal shearing stress is our tau sub B right there. So that's our FA and our FB right there if we do our summation of forces from our free body diagram from this element over here from AB. Now from there we can see, if we take a look at equations 3.44 and 3.55, from equation 3.44 what we can see here when we do out the summation of forces equal to 0, well our T sub A times TA right there is equal to T sub A times TB, because we take a look, set these equal to each other, we set them equal to 0, delta X and delta X go away on either side right there. You're just left with TA times tau A is equal to TB times tau B right there. So then we use this. We see that this expression is shown in equation 3.44 in our text. And then from there we see that this right here, our tau times T, our shear times our thickness right there is equal to our shear flow, or Q right there, from equation 3.45 in our textbook. And why we're left with just a tau times T right there, well, if tau A times TA is equal to tau A times TB, there's no real need for these indices A and B right there. We're just left with tau times T, which again from equation 3.45 in our textbook right here is equal to that shear flow. And what we can see from this here is that our shear stress varies inversely with thickness by this relationship. So now that we've taken a look at the forces, the next thing we want to do is compute the shaft torque. We can do this from looking at the integral of the moments due to shear stress right there. So for our moments due to shear stress right there, the first thing we want to do is figure out what are our moments acting on this here. So for that, we can go over to figure 3.51 for the shear flow in the member wall. We're looking at the side view there. We can see all the moment dm right there about O is going to be equal to this force dF times our perpendicular distance here, that P right there. So we can plug that in and say, okay, dm is equal to PDF, and this comes from equation 3.47. Well, what is our dF right there? Well, dF is equal to our tau dA, which is equal to tau times TDS. which is equal to tau t times ds, which is equal to qds right there. And this all comes from equation 3.46 back in our textbook right there. So plug that in. Okay, our df is equal to, again, we have now here this p times TDS right there, our tau TDS right there, plug that in right there, where this ends up being our QDS, so we can plug that in for our QDS, again, times that distance P right over here for the moment right there, which then is equal to our 2QDA right there. We're talking about this as our area right there from our area, or A from our area for shear flow right there. So then what we can do is we can take that as our torque is equal to the integral, so it's the integral of the moments right there of dm about 0, plug in this value right here from this relationship that we saw up there from 346 and 347 right there. It's the integral of 2q dA right there, which then is equal to, when we do that integral, of 2qa times a, and this is given by equation 3.48 in our text. So if you're interested in doing a little bit more of that derivation, please look back at equation 3.44 all the way through 3.48 in your textbook there for the derivation up to that there. Now from that, we can go from there and we can say that our shearing stress at any given point in the wall is going to be determined by the substitution of our Q from this equation 3.45 up here. We saw this relationship right there into equation 3.49 in our textbook right there. And then we end up with this as tau is equal to our torque T over 2 times TA, which is equation 3.50 in our textbook right there. So then we can get all that relationship from that there to get our tau. And then from there, if we did want to find our angle of twist, we do have the expression in our textbook right here of 3.51, where angle of twist is equal to T times L, our torque times that length right there, all divided by 4a squared times our g times the integral of ds over t. And again, this relates back to our equation 3.51 in our textbook right there. So if you want to look at a little bit more into the derivation of these equations, take a look at, again, equation 3.44 to equation 3.51 back in your textbook.